so it turns out I took up all of my little fancy room from that previous problem, but that's okay. So let me rewrite this of x plus 5 over 10x minus 7 equals 4x minus 3x plus 7. Okay. Well, at this point, we're not quite sure what the common denominator is, but I'm gonna write something real quick, and then we'll come back and ignore it. Well, let's actually start. Well, okay, yeah. So what I'm gonna do then is I'm gonna multiply both sides by 10x minus 7 and 5x plus 7, and that's that 8x plus 5 over 10x minus 7. And I'm going to slide this over so I get more space. All right, and then, so 10x minus 7, 5x plus 7 times the other fraction. Okay, now, I guess let me do the quick observation so that we can sort of get the panic out of the way, and then we'll come back and talk about what we can't multiply by. Okay, so when I did that, notice on the left side, the 10x minus 7s cancel out, or divide out, and I'm left with 5x plus 7 times 8x plus 5. And over here, the 5x plus 7s divide out, and I'm left with 10x minus 7 times 4x minus 3. Okay. Now, let me go back to the original problem. Because it was set up in a proportional setting, we could have just looked at that rule about cross multiply. Back in grade school, we used to take two equivalent fractions and we'd cross multiply, and then we end up dividing by something. A little more complicated in this case, but that whole cross multiply idea applies. But it applies because we can justify why it's okay to multiply by those two expressions. So I do need to, again, take a quick moment and pause and go, I acknowledge that I can do what I just did as long as it's a non-zero expression. So looking at 10x minus 7, the only time that thing would ever equal 0 is if x is 7/10. So that's what I'm saying, x will not equal 7/10. And the other thing that I multiplied by was 5x plus 7. So if I move that over, okay, so I am saying, before I do go any further, that I'm okay with what I just did mathematically as long as x doesn't end up being 7/10 or negative 7/5. Because if it does turn out to be those two expressions, then I have violated that multiply by a non-zero expression rule. Okay. So from here, I'm going to double distribute or FOIL, depending upon what you want to think of this. So it's going to be 5x times 8x and 5x times 5, and then the 7 times the 8x and the 7 times 5. So let's do that piece first. 5x times 8x is 40x plus 25x, I'm sorry, 40x squared plus 25x plus 56x plus 35. Okay, and over on the other side, when I double distribute or FOIL that, I get 40x squared, let's see, minus 30x minus 21x plus, I'm sorry, minus 28x, wow, plus 21. Okay. Now, what do we notice is consistent on both sides? They both have that 40x squared. So in essence, I can subtract off the 40x squared, so we kind of understand at this point that that's going to go away. When I combine like terms, here I get 81x plus 35, so that 25 and that 56 give me 81. And over here I get negative 58x plus 21. And then it's just a matter of adding and subtracting. I think we understand when I take the, let's take the 58. When I take the 58 and I bring it over, that it's going to be, I'm going to add 58. So 81x plus 58x. And then when I bring the 35 over, we're going to be subtracting 35 from both sides. So I think that will speed up some of us that are thinking, man, it's just being way too detailed. Then I need to figure out what 81 plus 58 is. And it's okay if you want to grab a calculator for that. That is 139x. And then 21 minus 35 is negative 14. And let's see, from here we want to divide by 139. So x happens to be negative 14 over 139. And that's a perfectly good answer. There's nothing wrong with that at all. Now notice it wasn't any of the two that we said I can't end up with. So there actually is a solution to this one, and it's just that interesting looking fraction. We'll call it an interesting looking fraction. So all right, the last little topic we're going to address in this particular lesson is solving what are called literal equations, equations that you don't even get numbers. They're just variable expressions, and we have to figure out how to manipulate those to solve for a particular variable. Okay, so in this first one, we have a equals p times 1 plus rt, and I'm trying to isolate out the r. Okay, so we're going to just make a little checklist as to what's going on here. I have multiply p, I have an adding 1, and I have a multiply r. Well, let's think about what do you do to undo those things. In that expression, how do you get rid of multiplying by a p? Well, we're going to divide by a p. How do you get rid of adding 1? We're going to subtract 1. How do you get rid of multiply by r? How do you get rid of multiply by t? We're going to divide t. Okay, and so notice what we did here. We sort of made a game plan for how to get access to that variable. And that'll work in this case because r is buried deep inside a set of parentheses, and it's buried deep inside a product. So I have to sort of, like layers of an onion, I have to undo each layer to isolate out the variable appropriately. So let's start with that first expression with the p on the furthest on the outside. So we said we're going to divide by p. So we get a over p equals, well, what's left is 1 plus rt. And so at that point we said we're going to subtract off 1. So a over p minus 1 equals rt. And then the last thing that we said we're going to do is we're going to divide by t. So a over p minus 1 divided by t equals r. Now, at that point, we technically have a perfectly good answer. We're technically done at that point. A lot of times, textbooks will keep going, so I'm going to keep going with this particular problem, but my goal was to isolate out r, and I've done that. So, on one sense, I've actually satisfied the question, but I do notice that I can make it pretty. Sometimes you'll see things like write it in the simplest form. And so I do see some fraction rules that I can apply that will give me a slightly more attractive looking answer. So I'm going to do that. But again, I'm going to go ahead and circle this. If our goal is to solve for r, that's it. That's fine. Now, couple of quick fraction rules that I can apply. I can take this 1 and I can rewrite it in terms of p. So I can take that to say a over p minus p over p. And it's still over t. And you're thinking, well, that didn't make it look prettier. It made it look worse. Well, hold on a second. Because the p's are a common denominator, then I can combine those together. So a minus p over t equals r. Now, we have this rule that says if you're dividing by a fraction, you multiply by its reciprocal. And all that's going to do is, well, you'll see. It's not going to do too much for our final answer here. But if I take that a over p minus p, dividing by t is the same as multiplying by 1 over t, which all that's going to do is put the t's together. P and the t together. So it's a minus p over pt equals r. And that's a little bit simpler looking of an answer. I know the argument some of you were probably thinking is, but it's a simpler looking answer, but it wasn't simpler to get. That wasn't what the goal was. The goal was to show you other ways to manipulate this. So if you, and actually take a look at the two expressions, that ap minus 1 over t, visually, do they look like they're the same thing? Well, it kind of depends on the person, but they actually are equivalent to each other, even though they have some slightly different looks about each other. But again, this first answer was perfectly fine. So technically you could have stopped there, and on the homework, if you input that answer, it should give you full credit, but sometimes you're asked to compare answers and they'll make you keep going. Okay, so this last question, a little different than last time. Last time it was the variable in question was buried in a set of parentheses, and so there was lots of things we could undo. Here we've got a little bit different of a concern, in that it's buried in the denominator of a fraction, and we're adding fractions together to begin with. But my target is this capital R right there. I want to be able to say R equals this. And so at this point, think about, what does this remind us of? Like, it would be really nice. It would be really nice if it said R equals 1 over R equals a number. Let's just say it said that equals 5. If I was then asked to solve for R, what would I do? Well, I could multiply both sides by R and then divide by the 5, or I could just do the reciprocal trick. So if I take those two things and swap them out, so if I put that over 1, then that would say that R happens to be 1 over 5. So if I can get it 1 over R equal to something, then I can just do this reciprocal idea to end up isolating out R. Okay, so there's my interim goal, is to get the right side to be a single fraction. Okay, so let me kind of bring this down here. This is what we really have, 1 over R1 plus 1 over R2. Okay, so what our denominator rule says, if I have, what would my common denominator be? And that would be R1, R2. So this first fraction, and actually, let me pause here. Let me just pause for just a second, and let's do this. 1/2 plus 1/3. How would you work that? What would you do to get that answer? Well, I would rewrite the 1/2 as 1, over 6. So I'd multiply the 2 times the 3. So I'd get 3 over 6, which is equivalent to 1/2. And I would multiply the 2 times that 3, so 2 over 2 times 3, so it'd be 2 over 6 plus 3 over 6, right? And then I would just, since the denominators match, I would just add the two numerators together. Okay, so, and it's okay to do this in math, is if you can't quite see with variables, with letters, put numbers in there and say, well, what would I do if there were numbers there? What would happen? And when we added these two fractions that had different denominators, we ended up multiplying the two denominators together. But notice, this number came up top, and that number came up top of the second fraction. So if I do that same trick over here, when I multiply the two denominators together, I get an R2 over here and an R1 over here. Okay. Then, what next? Well, we now have it 1 over r equal to a single fraction. And what do we say we're going to do if we get it equal to a single fraction? We're going to flip it, get the reciprocal. So we get r equals r1, r2 over r2 plus r1. And at that point, we are done. That's about as simplest form as we can get. One idea, and I'm just going to say this just to give you some sort of hope. So let me kind of zoom out here so we can see this in its entirety. You know, because whenever I work this problem in a face-to-face setting, I always get students with that wide-eyed, you know, that look of, oh my goodness, you expect me to know this? You expect me to come up with this on my own? And the answer is nope. I don't expect you to come up with it on your own. I expect you to remember it and be able to put it on paper later. We call that regurgitate, math puking, I guess. So imagine after you saw this video and you saw this problem, if I asked you to rework that same problem, could you do it? And if the answer is no, watch the video again. And watch it as many times as it takes for you to go, okay, so if you ask me to do this exact same problem again, oh, I can do it from memory. You know, because that's what I'm having practice on homework, is rewriting similar looking things using the same process. Now imagine your roommate or your spouse or your, whoever's at home with you comes in and they also are taking college algebra and they haven't done this problem yet. And you've practiced writing it about 3 or 4 times, so you have the process memorized. What would they think when they show this problem to you and you just write it out from memory? What would they look at you and think? They would think, oh my, this person's just a genius. They know what they're doing, right? And at that point, you have a choice. You can fess up and say, well, honestly, my professor just showed me how to do this. Or you can take credit for it and go, well, yeah, I am that smart. And that's either one is fine. But notice how that feels. No matter what you end up doing, it feels great to take something that's complicated and hard and be able to produce positive results with that. So as you're looking at homework, that's the goal, is to take a common process and make it something that's a little more manageable for you.